Dear students, we are starting with another lecture on Transportation Engineering 2 course. This lecture pertains to the wheels and axles and their configurations and the associated feature of wheels, that is coning of wheels. In the previous lecture we have discussed about the gauges, the various types of gauges being used in globally or in India, the problems associated with the gauges and the uniform gauge policy of Indian Railways. In today's lecture we will be taking up the wheels and axle arrangements, the track capacity, coning of wheels. These are the three major important points which we will be covering today. There is associated feature of coning of wheels, that is adding of sleepers, will also be taken up in short. Starting with the wheels and axles. In the case of wheels and axles, we have the different types of the locomotives and the wagons which are used for the hauling of passengers and freight. All these wagons or locomotives have different specifications depending on the gauges for which they have been used. If we look at the various locomotives from the very starting of our history, we have been using steam locomotives and then they have been replaced by diesel locomotives and finally by the electric locomotives. We are not talking about the most innovative design features of the locomotives which have come into play in the recent past, where we are in position to attain the speeds of as high as 250, 300 or 500 kilometers per hour. Now here we are talking about the initial three versions of the locomotives, that is the steam locomotives, diesel locomotives and electric locomotives. In the case of steam locomotives, the wheels and axles are classified by the basis of weight system. Traditionally, steam locomotives have been classified using either their wheel arrangements or sometimes they have also been classified on the basis of axle arrangements. In the case of the wheel arrangement classification, they are being classified on the basis of weight system. Under this system, the locomotives has three different types of wheel bases. They have the wheel bases which are either coupled or which are having the driving conditions or the tractive power attached to them, or they are the wheel bases on which no tractive power is attached. In such cases where the tractive power is not being attached, on the basis of the location where they have been placed, they can be termed as the leading wheels or the trailing wheels. Taking this type of classification based on the leading wheels or the trailing wheels or the coupling or the condition of the wheels where the power has been attached to the wheels or not, we can have the classification is that the locomotives leading non-powered wheels, the driving wheels which are usually coupled but in some cases they may not be coupled also, and the trailing non-powered wheels. All these three categories of wheels have to be separately indicated in the weight system. Now when we take the Indian practice, the Indian practice has been taken from the United Kingdoms because the British were the persons who have introduced the Indian Railways in our country. In this system, we count wheels and we do not count the axles as far as the steam locomotives are concerned. In the case of steam locomotives, one example is being taken here where it is being shown as 242. Now this 242 has the significance in terms of the wheel bases as being defined earlier. The first two is the front wheels or the two number of wheels have been placed, or what we can say is that there are one axle which is being placed in the front condition. Then the four pertains to the four number of wheels which have been placed in the central condition where they are the powered wheels or the driving wheels, and therefore they transforms into the two axle condition. And then there are the trailing wheels where we have two wheels at the back, and again if we transform them into the axial condition, it will be pertaining to one axle. So if we are interested in transforming this from the wheel condition or wheel count to the axial count, then it will be nothing but 1, 2 and 1 instead of 2, 4 and 2. Now when we are talking about the steam locomotives requires a certain storage area or the tank where the coal can be stored, because this is the prime condition which is required for the movement of the steam locomotives. In such cases, a suffix is also used to indicate the type of the tank which is provided on the steam engine. In the case the tank engine is being provided, then it is indicated using the alphabet T. If it's a saddle tank, then it is denoted as ST. If it is well tank, then it is denoted as WT, and if it is pannier tank, then it is denoted as PT. Likewise, there are other cases too. Now we take an example of a compound locomotive. The compound locomotive is a condition where there is a more tractive power which is required to haul the passengers or the freight. Generally, this is a condition which is found in the case of the freight transportation. A heavy amount of freight which is to be transported, and the terrain conditions governs a condition where we require to provide two locomotives together so as to haul them. Here this is an example of that compound locomotive where two locomotives of condition 282 or 284 have been joined together so as to haul the traffic or the passengers or the freight. Again, if we go by the white condition or white system of classification of the locomotives or the wheel configurations, then 282 means we have two front wheels, 8 medium or central wheels, and 2 trailer wheels in the case of the first locomotive, whereas in the case of the second locomotive we have 2 front wheels, 8 central condition wheels which are electrically driven, which are driven for the movement of the locomotive, and then in this case we have 4 trailing wheels. Now there are other conditions too where a locomotive may have 2 or 3 sets of coupled power driving axles. Now in such conditions, how we are going to define them or how we are going to categorize them, some of the examples again show such type of conditions. Here the example has been taken is 2882. This 2882 indicates that there are 2 sets of 4 driving axles. When we say there are 2 sets of 4 driving axles each, it means we are having 8 wheels in one set and then the 8 wheels again in the other set. That's why in the central location we are having 8 and 8. Still we have 2 trailing and 2 front wheels being provided which are not being given any driving condition or they are not being coupled together. Similarly, there is an example of 2, 6, 6, 6 and 2. In this case there are 3 sets of 3 driving axles each. So these are the different types of the classification systems which are there for the steam locomotives depending on the type of the condition or the type of the locomotive we are using, and these type of the locomotives are going to be selected on the basis of the total amount of traffic or the total freight which needs to be transported. Now we can also look at the European arrangement. The European arrangement says that they count the axles then the wheels. As we have taken the example previously where it was 242 condition where the wheels were counted with the 2 front, 4 central and 2 trailing wheels. Here in this case it will be transformed into 1:1 where there is 1 axle in the front condition, 1 axle in the trailing condition, and there are 2 axles which have been connected to the power. So that's why it is 1:1 or 1-2-1. Similarly, there are other conditions too like 1v1 and so on. Now coming to the diesel and the electric locomotives. In the case of diesel and electric locomotives, the wheel arrangements are more or less similar in nature. In these cases, the powered axles are described using letters and unpowered axles, if any, they are indicated by the digits. Now in this case, the various digits which we are using have been shown here. We can use A, B, C and D depending on the type of the conditions for which the vehicle or the locomotive or the wheel arrangement has to be identified. In case we are using A, it means it is single powered axle on a bogie. A bogie is a base which is provided at the base of the locomotive which provides the motive power to the locomotive. Therefore, the locomotive has 2 structures. One is the upper structure on which the rest of the things have been placed, and there is a bogie which is a supporting structure which has a powered axle and through which it will be moving. Similarly, there is another case which is termed as BO. BO means there are set of 2 independently powered axles on a bogie. these two independently powered axles on a bogie, they are not a coupled condition. In the case of the coupled conditions, the same power will be used to transfer the traction to the axles which have been attached to it, whereas in this case the power will be given separately to the different axles. Similarly, the third condition is CO. In the case of the CO, the set of three independently powered axles are placed in the same bogie. Then DO or D, it denotes a set of four powered axles. So this is a case where we are having a single bogie condition, and in that single bogie condition these abbreviations have to be used. In case we are having more than one bogie system, there are two bogies or the three bogies being placed for the same locomotive, then the combination of all these alphabets can be used. We will be looking at those combinations also in a little while. Now this characterization which is being shown on this slide again pertains to the diesel and electric locomotives where the combinations have been shown. In the case of a combination where the two bogies are being placed with each bogie is having two separately powered axles, then it is transformed, or this is indicated by BO and BO. When there are three such bogies being provided with the same locomotive, then it is a condition BO, BO and BO. Similarly, if there is a bogie in which three powered axles conditions have been provided on each bogie set, then it's a CO condition, that is there are two bogies being provided with three powered axles. So this is a combination condition which is being transformed into some indicative values. Now there is also a condition where instead of using BO we can use simple B. When we are using simple B, it indicates that the axles are not independent but they are coupled mechanically, and so that the same motor drives all the axles in the bogie. So this is another condition, another sort of a wheel arrangement which is provided for the diesel and electric locomotives. Now in this diagram what we can see is that all the three conditions have been shown. There is a condition where the first condition, it is BB condition. When it is a BB condition, it means there are two motored axles driven of the same motor, or they are the coupled condition. Then there is a BO condition where they are the independent motored axles being provided, and then there is a CO and CO conditions where again it is an independently motored axles being provided in this case. What we can see in this one is that in this case where the coupling is being provided, they have been shown the two wheels, one at this point and one at this point, or at one end this point and one end this point, they have been jointed together by a broad or firm lining. Whereas in the case of the BO and BO condition, they are not being joined by a firm lining, they are being joined by a hollow lining condition. So we have again the two wheels, one on this one on this one. It means there is one axle on this side, one axle on this side. Similarly, one axle on this side and one axle on this side means this is one bogie set and this is another bogie set which is being provided for the same locomotive. And then there is a power which is being transformed from this power set to the this wheel or axle, or this wheel and axle condition independently. Whereas in this case the power is coming centrally to these one and then it is distributed to both the axles condition. The same is the condition in CO where we are having three axle conditions and we are having two bogies. So this is one bogie and this is another bogie, and then we have wheels like one wheel, second wheel and the third wheel. So similarly on the other side. This is another diagram which shows the condition how the two wheels or axles have been combined together in the coupled condition, and there is the same motor which is providing the tractive power to the two wheels bases or the axles. Here what we can see is that there is a motor pinion being provided at the center somewhere here. Then there is a traction motor which is being placed at this level which provides the total motive power to the vehicle. Now from this motor pinion the power has to go to the wheel, so that's why there is an intermediate gear wheel system which is provided, which connects the motor pinion with the wheel main gear wheel system. So this is a main gear wheel system which is being connected here on this side and this is being connected here on this side. Now this is one axle being provided here, this is another axle which is being provided here. They are the driving axles, or in the center we can see the axle. So this is one bogie set. In this one bogie frame, the two wheels bases have been provided along with the coupled condition. So that is how it is being shown, the coupled condition. When we show diagrammatically, then what we do is we just join them by a broad lining. Now this is another condition where the combinations can also be used, like we have a 2BO/BO2 condition which says that there are two front wheels and that there are two trailing conditions, and then in the center we have a BO and BO, that is that two bogies have been provided with the independent wheel or axle systems. This is 1D1. 1D1 means the four axle conditions have been provided in the same bogie set, and there is a one front and the one trailing axle condition. Similarly, 1CO/CO1 is another condition wherein there is a one front and the one trailing axle being provided, that is they are being shown in the white color, and the CO/CO condition that is being provided in the reddish color, where again in this case there are two bogies, one on this side and one on this side, and the same bogie again there are three wheel axles being provided in each of the bogies. Then this is A1A system, where again we have there is a one central wheel which is the front or the trailing wheel, and then there are the two rad wheel axles which have been provided on the two sides. Again they are again in the independent condition, they are not being coupled together. Now in this case of the wheels and axle arrangements, the multiple unit locomotives are indicated by parenthesizing the unit specifications and prefixing a number corresponding to the number of units. It's a condition where the same site of a locomotive is being used in double or triple. If that is a condition, that is if there are two unit locomotives and each unit of locomotives having one unpowered leading axle, one unpowered trailing axle and four coupled powered axles, then they are going to be denoted by twice of 1D1 nomenclature. 1D1 is the specification of the locomotive, and when we have placed twice, it means we are using two locomotives of this specification so as to haul the freight or the passengers. Now this was all about the different types of the wheel or the axle arrangements which can be used in the steam locomotives or the diesel locomotives or the electric locomotives. Now once we have this idea of about the different types of configurations, now we come to the other aspect of the tracks, that is the track capacity. Track capacity is defined as the number of trains that can be handled or run safely on a track per hour. It means depending on the number of tracks which have been provided or the number of directions in which the traffic can be moved, we can talk about the number of trains which can move per direction per track. When we have this data in hand, then we can find out that how many trains can move in either of the direction or in both of the directions taken together, and that is going to be defining the total track capacity of that section. Now in this track capacity, the one important aspect is, and it always remains there so as to achieve more of the revenues and so as to become more revenue generation condition, is that we have to enhance the capacity. Now there are certain ways by which the capacity can be enhanced. The two of the things which are more important have been listed here. One case is that we can achieve a faster movement of trains on a track, and that is we are increasing the speed of the trains, and if we can increase the speed of the trains, it means the track capacity can be increased because we can move more of the trains on the same track. The other condition is decreasing the distance between the successive trains. It has another main safety emphasis here or the aspect here, because if you are decreasing the distance between the two successive trains which are moving in the same direction on the same track, then there are all chances of hazardous conditions coming up. Therefore, the main emphasis here remains is that how we can maintain a safer distance between the two trains so that no such hazardous condition is coming up. Now we will be trying to look at certain measures by which the track capacity can be enhanced. As we have seen the two cases, we will be taking up these two cases one by one, and then we will be trying to look at certain measures which can be taken so that the track capacity can be increased. Now here in this case, the measure to increase track capacity is being taken by increasing the speed of the trains. Now, what may be the different ways by which the speed of the trains can be increased? The one is that we can make the trains to move at the same speed on all the tracks. When the trains are moving with the same speed, then there is chances that we will be having more efficiency than the normal conditions. But then again, this is not a possibility at all together in the most practical conditions. When all the trains are moving at the same speed, then there is going to be a problem for the stopping of those trains on the intermediate stations. As soon as there are a large number of intermediate stations, the same amount of speed and the maintaining that speed will be a bit difficult condition. Therefore, what is required is, in this case, the first aspect which needs to be done is that we have to maintain the gauges uniformly, and we have to provide the tractive powers as uniform as possible. One thing which is being done in that direction is the use of diesel or electric traction instead of the steam locomotives, which have been used from the initial starting. The electric traction or the diesel traction can be used so as to provide the higher speed conditions as compared to the steam locomotives. Of course, today with the technological advancements, a large number of techniques have come by which we can achieve the speeds as high as 500 kilometers per hour. But that is not the scope of discussion in this lecture. We will try to look at this aspect in some other lecture where we will be looking at the high speed movements of the rails or trains. Another aspect of increasing the track capacity is in terms of the removal of the speed restrictions. But this removal of the speed restrictions can be done only if the geometrics of the sections have been maintained in a most regular fashion. There is no such condition where the geometric restricts the speed by itself. If that is a condition, then the geometrics have to be rectified. Another thing is that improving the existing track. Of course, improvement always has the scopes of improving the things. If we can go for an improved track condition which is being maintained periodically, there are all chances that the speeds can be maintained on those tracks, and there is not going to be a problem of again and again stopping the trains for the purpose of the maintenance of those tracks. As and when there is a maintenance of the track and the vehicles or the trains still remain moving, then what we found is that we have to reduce the speed of those trains which are moving on those tracks. So this is another aspect of increasing the track capacity. Next aspect is the reduction in the time of stoppages of the trains. What we found is that at number of stations the trains have been stopped for a longer period of time because of certain reasons. We have to identify those reasons and we have to find out the ways by which those stoppages can be reduced and optimized. If we can do that, then the total journey time will reduce and it will increase the overall journey speed. The better coordination for change of the direction of train at junction is another aspect where we found that the most of the time is being lost as soon as the change in the direction is required. Whenever there is a change in the direction, what is being observed is that we have to use the same locomotive if the new locomotive is not available at that junction station or the station where the direction is to be changed. In that case, what we have to do is we have to make a turnaround of the same locomotive which has brought the train at that location, and then it will come to the another location of the train, that is the rear end instead of the front end, and it will be taking the train along with it, and it takes certain amount of time. So that type of delay needs to be optimized again by the provision of either the other locomotive or by providing a mechanism by which this sort of a thing can be done in a much faster way. Electronic control and signaling arrangement is another aspect of increasing the track capacity. If we have the most modern ways of signaling systems or the electronic control systems by which we can find out the movement of the trains on all the tracks, then there is a possibility of reducing the distance between the two trains which are moving on the same track in the same direction, still maintaining the safety and now increasing the track capacity. So these are some of the aspects which are associated with the increasing of the track capacity, and they have also some effect on the speed of the movement of the trains on the same tracks. Now we come to the other aspect, that is reducing the gap between the trains. what may be the different ways by which the gap between the trains can be reduced. One such system is the multi-aspect signaling system. In the case of the multi-aspect signaling system, we can provide a lesser distance between the moving trains on the same track. We will be discussing about the multi-aspect signaling system when we will be taking up the signaling system or the safety control systems of the operational of the trains on the tracks in some other lecture. Another aspect is decreasing the length of section. When we talk about the decreasing the length of section, it is done in terms of providing an opportunity for a vehicle, for a train which is moving at a higher speed and which requires a section where it can overtake the other speed which is train which is moving at a lower speed. So in this case, when we have decreased the length of the section, such opportunities will increase. If such opportunities cannot be increased by the lowering of the length of the sections, then the next thing which can be done is increasing the length of crossing sections or the loops. If we have increased the length of the crossing sections of the loops, again the feasibility of overtaking a slower moving train by a faster moving train will increase, and that's how we can provide a much faster services as compared to the normal conditions. And when we are having much faster services, in this case it means we are increasing the track capacity. The next way of doing it, which is a little more capital oriented, is increasing the number of tracks or lines. It means if there is a requirement or there is a heavy traffic which is moving in a certain direction, then the one thing which is to be done is to provide multiple tracks in the same direction, but then it requires a large amount of resources. If the resources are available, then the other aspect which needs to be checked is the amount of land available to us for such type of development. So there are certain interrelated aspects in this case, therefore it's a little difficult so as to increase the number of tracks every time so as to increase the track capacity. Interlocking of sections and yards is another aspect. At most of the places now on Indian Railways, we are having these interlocking facilities. Therefore, by provision of those interlocking facilities, we have the potential of changing the trains from one lane to the another track, and that's how the loop conditions can be created and the trains can move at a fast, faster and efficient movements can be achieved. The next step which is being defined here is the use of centralized traffic control system. This is related to the operation of the trains. This is also a safety measure, and it relates to the total signaling systems which are being provided along with the interlocking systems which are provided along the sections between the two major stations where the centralized traffic control systems have been provided. In this case of centralized traffic control system, what we do is that we are sitting at one place with a big panel where the whole of the section has been shown, and the movement of the trains are also depicted on different lines or the tracks which have been provided in that section. So therefore, while sitting at one place only, we can find out the total movements of the trains or different tracks, and then from there itself we can control those movements by the operation of signals or by interlocking the different tracks. Again, we will be looking at this aspect in a little more detail when we are taking up the signals and the controlling systems. Now some of the related aspects to increase the track capacity have been listed here. One is the optimizing the yard operations. In the case of the yard, there are a number of operations which are carried out. If it's a big yard, then the operations remains like the receiving of the train, the sorting of the train, the dispatching of the train. In other cases where the maintenance facilities or the servicing facilities have been provided, then we have the maintenance yards or the locomotives yards where the maintenance of the locomotives or the servicing of the wagons are taken up. All these aspects take a lot of time. Now, if we have to optimize these time networks of the different activities which are performed in any of the yard, then probably again we can increase the track capacity. Another thing is revising the standards to permit higher speeds on main tracks. As we have seen the IR Indian Railways specifications in one of the lectures, we have the broad gauge, meter gauge and the narrow gauge conditions, and within the broad gauge conditions again we were having the 5 categories as A, B, C, D and E. In the case of the A category of the broad gauge condition, what we have seen is that the speed can go up to a value of 160 kilometers per hour. Now if we can improve our standards so that we can permit higher values of the speeds on the main tracks specifically, then also we can increase the track capacity. The work is going on in this direction. Probably in some period of time we will be having new specifications relating to high speed tracks. Adopting safety measures and telecommunication facilities for better movement is another way of improving the track capacity. And the availability of relief mechanism in case of the mishaps is another way of increasing the track capacity. If there is any accident which has taken place, then how fast we can clear up the tracks, how fast we can provide the relief. That's another way by which the track capacities can be increased. Now, after looking at the aspects of the previous one, that is we have seen about the track capacity, how we can increase the track capacity. The next associated feature with the wheels and the axles is the coning of wheels. Now here in this case we are looking at the two conditions. There is one wheel where the flat surface has been provided like this and like this. This is the axle being placed here, which has a connectivity with another wheel on the other side, and this base is being provided with the flanged condition on this side like this, which is protruding outside on this side and protruding outside on this side. So this is a flat surface condition, and there is another condition where the wheel is being coned like this by making a taper at this side as well as making a taper at this side, and the rest of the things, that is this diameter or this axle condition or the flanged conditions, they remains the same. Now if we look at this rail sections which have been provided at the bottom on which these wheels have to move, what we found is that these rail sections will come like this, and therefore in this case there is a continuous connectivity of this wheel base at this position, as well as if we look at this side, there is also the continuous connectivity of the flange with the rail head at the side. Now when we are having this type of flat surface condition, or when we are having this type of a tapered surface condition, what is going to happen? In the case of this flat condition, we just think about a wheel condition of any vehicle or a road vehicle which is moving on any road. If we take that tire, the tire has this type of condition where it has a flat base, and through that flat base all the loads get transferred to the rail section. But then they remains at the same location, whatever is the location being provided in that case. Therefore, there are certain problems associated with the flatter surfaces in the rail sections, because the rail section, as we found here, is a steel section, and this is also a steel wheel base which is provided, and therefore the interaction of these two creates large many stresses at this location as well as at this location. Whereas in this case there is a sort of a slipping condition which gets created, and this wheel keeps on moving this way or this way, that is in the lateral directions. So we will try to compare whether we can provide this flat surface wheelbase or we have to provide this cone surface wheelbase in the coming slides. Now what we look is that there are certain problems associated with the flat wheel. One thing is that because of this condition where the flanges have been provided, there is a small distance between the flange and the rail head. Due to this small distance between the flange and the rail head, there is a lateral sway which is provided on the track. You must have also observed yourself when you have been moving in any train that the train compartment vibrates in the sideways directions. When that compartment is moving in the sideward direction, that is what is the lateral sway which is coming. As soon as there is a lateral sway, what happens is that it will create a condition of the wearing of the flanges. At the same time, it will also create the wearing of the side of the rail heads. So this is one of the drawbacks of the flat wheels. Another condition which we can look at is in terms of the curved sections of the tracks. In the case of the curved sections of the tracks, if we take the radius of the curves of the two rail sections which have been placed parallel to each other on the curved section, then what we found is that the radius of the inner condition is smaller than the radius of the outer condition, and therefore when it transforms into the circumference, there is a more distance which needs to be moved on the outer rail condition as compared to the inner rail condition. And it means In such condition, when we are having the flat wheel condition, we cannot do this, because in the case of the flat wheel condition, the circumference remains constant whether you are very near to the flange or you are away from the flange. When the diameter remains constant, it means the circumference movement which will be there in the one rotation of the wheel will also remain constant. Therefore, there cannot be a distinction in the distance being moved on the inner rail or the outer rail or by the inner wheels or the outer wheels of a wheelbase. When this flexibility is not available due to the rigidity of the wheelbase, then we have to look at certain other options by which we can get some advantages of the movements using the wheels only, and that is what is being provided by the coning of the wheels. The coning of the wheels causes on a straight track, what it does is that because it is a cone section, as we have seen in the previous one slide, so in that cone section, as soon as there is a lateral sway in any of the direction, there will be an increase in the diameter, and because of this increase in the diameter, it will try to revert back to the average diameter condition, and that is where the slipping of the wheel will take place. When the slipping of the wheel takes place, it will finally come to the equilibrium condition where the average diameter on the outer rail as well as on the inner rail will become same. As soon as they are both equal, then it is a straight track condition where the train, where that vehicle will be moving on those rails in a uniform condition. Now, when we look on the curved track condition, what happens? When we are talking about the curved track section, there is a centrifugal force which acts in the outward direction. When there is this outward directional centrifugal force is acting, the total track, the total compartment will try to move in the outward direction laterally. So, when this type of a movement takes place, what will happen is that on the outer rails the diameter will increase, whereas on the inner rails the diameter of the wheel will decrease. When this type of diameter is increasing on one rail and diameter is decreasing on another rail, the circumferential movement being moved in one rotation of the wheel will be different. Due to this differential wheel movement of the two wheels on the inner or the outer condition, we found that there is a more distance which is being traveled on the outer track as compared to the inner track, and that's how, because of the coning of the wheels, we can achieve what is required. Now, in this diagram, we are trying to show the same two conditions. This diagram shows the straight running condition. We have this as a wheel which is having a coning conditions in this direction. Similarly, we have a coning condition in this direction, and these are being jointed together by an axle in this way. At the center location of these wheels on these coning surfaces, we have the average diameter condition, or what we can say is that this is A and B, which has been shown here, the average radiuses of the wheels which have been connected on the same axle. As far as there is a straight running condition, the straight running can be achieved only if both of the wheels are moving the same distance in one movement or one revolution of the wheel, and in that case this is possible only if that this radius of this wheel, that is A, and the radius of this wheel, that is B, they are equal to each other. There is another condition in this diagram where we are taking our curved section. In the case of the curved section, we are assuming in this diagram that the centrifugal force is acting towards the left hand side because the track is taking a turn towards the right hand side. So, if that is a condition which is happening, this whole wheel base will move in the laterally towards the outer direction like this, that is towards the left hand side. When this movement is taking place in this direction, then what is happening is that the diameter of the wheel on the left hand side will increase on the rail section, whereas the diameter of the wheel on the right hand side rail section will decrease. It means here the B is greater than A. When B is greater than A, then the more distance will be moved on the outer rail this side, whereas the lower distance will be moved on this side, and it shows that when B is greater than A, it is taking to the right turn. So, this is what is the advantage of making a coning of the wheels. So, as soon as we have done this type of a coning of the wheels, we can achieve the different types of the movements which can be there in sections which are provided on any of the track. Therefore, what happens is that the coning helps in controlling differential movement of front and rear axles caused due to the rigidity of the frame and axle, and thus acting as a balancing factor. In the case of the curves, what we have seen is the rear axis has tendency to move towards the inner rails, and that is why there is we have to control this type of phenomena. If we are not controlling this type of phenomenon, then there is another condition which gets created as a derailment of the trains. The reducing the wear and tear of wheel flanges is another condition, because as soon as the diameter increases on one side, it tries to come back to the equilibrium condition, and equilibrium condition means it tries to come back to the average diameter condition. So therefore, as soon as there is a lateral sway and the wheels or the flanges strikes the rail head on the outer wheel condition, it will start reverting back because of the coning of the wheel. As soon as it starts reverting back because of the coning of the wheel, there will be lesser amount of wear and tear of the wheel flanges. And because there is a turning of the tracks and the coning of the wheels is helping us to attain the differential movements, so therefore there is a smooth riding which will be attained on the track. Now in this case, this is a diagram which is trying to show that what is happening when we have a rail section which is being provided in this form, where it has a horizontal surface at the top one, and we have the wheel where the cone surface has been provided like this. Now suppose this wheel is having a lateral sway, either it is moving towards the right or it is moving towards the left. This is how it is having an increase or decrease in the diameter on the rail head. What we can find here is that there is a concentration or localization of the stresses at a certain point on the rail head. When this concentration or centralization of the stresses is happening, then there will be more wear and tear at this location where this type of connectivity will be taking place. At the same time, because this connectivity is not there uniformly at this position, there is an eccentricity which will get created in this rail head. So if this type of eccentricity is getting created, it will create a problem to the rail sections, because there will be some bending which will get created because of the eccentricity in this one. So we have to look at these aspects in this case, because the coning of the wheels also creates some problems, and we have to rectify those problems so as to achieve a condition where everything remains constant, where everything remains in the equilibrium condition, and the comfortable journey can be attained. So what we can do is, we have to look at two things. What are two problems which are there? One is the wear and tear due to the slipping action. The slipping action is defined in terms of the slip of the wheel, which is governed by the angle which is being made by the rigid wheel base at the center of the curve. Here the theta is being shown as that angle. So if we have this theta angle, therefore there is the movement which will be there as 2 pi theta with respect to the 360-degree turning of the wheel, and g is the gauge, then this total value of 2 pi theta divided by 360 multiplied with the gauge value gives the slip of the wheel. And this slip of the wheel in the case of the broad gauge condition is equivalent to 0.029 meters per degree curve. So because of this slip of the wheel condition, there is a wear and tear action which will be taking place. And as I have just told you that in the previous diagram, there is an eccentric loading on the rail sections, and this eccentric loading on the rail sections causes bending or buckling of the rail sections. Therefore, we have to remove all those conditions. So there is certain measures which needs to be taken with respect to the rail section, because the coning is already being provided on the wheels. And that is what is known as the tilting of the rails, and the associated feature with that one is the edging of sleepers. In the case of the tilting of the rails, what we do is that the rails are tilted at an angle of 1 in 20. This angle 1 in 20 is the same angle at which the wheels have been coned. Therefore, as soon as we have the rails being tilted at an angle of 1 in 20, the topmost surface of the rail head will come into contact with the base surface of the wheel, and therefore there will not be any localization of the stresses. The whole of the stresses will be transformed or transferred by the total amount of the contact area which will be there, and now in this case the total amount of contact area will remain the whole of the rail head or the whole of the width of the wheel of the train. Now in this case, as soon as we have tilted the rails at an angle of 1 in 20, what are the controls which will be achieved? One control is that the lateral bending stresses due to eccentric loading will be removed, they get eliminated. Because in this case now there is no eccentric loading, therefore there is no chance of bending taking place or buckling of the rail taking place. It also reduces the wear and tear at the inner edge of the rail as well as on thread of the wheel, as we have seen in the previous diagram, where in the case of the horizontal rail section there is a central one point at the side of the rail head where the wearing was taking place, and this was the threading of the wheel was also becoming at that location only. If we have provided the tilting of the rail sections, then it will reduce the wear and tear in this case. Now once we have done the tilting of the rails have their foot, and this foot is placed on the sleepers, and then it is tied to the sleepers using the fastenings. Suppose the base of the rail is being tilted, then again what is going to happen? In this case again there will be the same sort of conditions as we have seen in the case of the coning of the wheels, but is still not making a tilting of the rails. As soon as the base of the rail is being tilted, there will again be a localization of the stresses at one point, and because of this localization of stresses at one point, there will be more stresses being induced, a hard stress is being induced, and the indentation will take place in the sleeper. If the indentations are of a much higher value, then it may also crack the sleeper at that location, but that's a failure condition which may be achieved at a much last stage. So therefore there is another thing which is done, which is known as edging of sleepers. Edging of sleepers means there is a groove which is being cut at the base of the rail head, and this groove is also having an angle of 1 in 20. Therefore in this case, when the angle is 1 in 20, what will happen is the rail base will get seated into that groove. Now we will look at this diagram and try to correlate the tilting of the rails and the edging of the sleepers in this diagram. Here this is a wheel, this is the flange, this wheel is having a cone condition, and this angle is 1 in 20. This wheel is being connected by the rigid wheel base to the other wheel on this side, which is also coned at 1 in 20. In the case of the tilting of the rails, if you are not doing the tilting of the rails, then the rail head will remain horizontal like this, and therefore there will be only a single point of contact at this location. Whereas now as the rail is being tilted at 1 in 20 angle, therefore this whole of the surface is in constant touch with the wheel base. Therefore the total amount of stresses or the loads are going to be transferred through all of this section. Now the other aspect which we are looking is the edging of the sleepers. If we have tilted the rail section like this, then the base of the rail section will also get tilted, and in this case if we are providing the straight sleeper like this one, then again at this location there will be penetration of the rail into the sleeper. That's why what we do is that we provide the tilting of the sleeper base also at this location. This may be in the form of a wedging, or maybe in the form of making a groove in this location, or providing a chair wherein this rail is being seated into the chair which is attached to the sleeper so that it remains fixed in location. And this sort of an angle making in the sleeper so as to seat the rail is known as edging of sleepers. So therefore we have a tilting of the rails. Instead of straight forward like this in the vertical direction, it is being changed to this one at 1 in 20. Similarly here, instead of having it as a horizontal condition, it is being transformed in 1 in 20. So this is about tilting of the rails and edging of the sleepers. Now the next thing which I am interested to take today is about the permanent V. Though I was interested in taking up this one in the previous one, but because of shortage of time we could not take it. We'll just try to look at some of the aspects related to the permanent V. In the case of the permanent way, it is defined as the railroad on which the train runs. Or in a more detailed form, we can define it in the form of it consists of two parallel rails which are placed at a specified distance in between them and which are fastened to the sleepers, which are embedded in a layer of a ballast of a specified thickness spread over the formation. It means any permanent way consists of certain components, and those components are the rails, the sleepers, the fastenings, the ballast and the formation level. So, if we take all these things together, that is constituting a permanent way. So, we try to look at what are the requirements of any permanent way. In the case of any permanent way, as we are looking at the different components, the very first component is the rail, and the rails have to be placed at certain distance parallel to each other, and that distance is nothing but is defined as gauge. Therefore, in this case the gauge should be correct and uniform. If the gauge is not correct or it is not uniform throughout the rail section, it will cause derailment of the rails. Another aspect related is the cross levels of these rails which are being placed at the gauge length, gauge distance. Here we have two conditions. The one condition is related to the straight track and another condition is related to the curved section. In the case of the straight track, the cross levels of both the rail sections has to be maintained at the same level. Whereas in the case of the curved section, the cross levels will be different, and the cross level of the outer rail with respect to the inner rail will be at a distance higher by that one at a value of super elevation. We will take this super elevation, we will discuss the geometrics of the railway tracks. Next aspect is related to the alignment. Alignment has to be straight as far as possible, and it should be free of the kinks, because the kinks are the points of weaknesses. At the same time, they are the points of discomfort created to the passengers. The gradients needs to be uniform and gentle as far as possible. If they are uniform or they are gentle, in that case we are going to achieve a more comfortable journey than otherwise. The next point is the resilience and elasticity of the track. The resilience and elasticity of the track is another important aspect, because there are large amount of loads which are coming from the top and which are transferred through the rails or the sleeper to the ballast section or the formation level. So, if the track is not resilient and it gets deformed because of the loads which are coming from the top, then it is going to fail in the very short period of time. So, that is why it is very important that the material which we are using is resilient and elastic in nature as far as possible. Another aspect associated with the requirements of the permanent way is drainage. Drainage has a direct consequence on stability. If there is more of the drainage, it is going to be detrimental to the life of the materials which have been used in the construction of the permanent way. Therefore, it is required that there is no waterlogging around the permanent way, and the water should get drained as fast as possible. Lateral strength is another important aspect. As we have seen in the case of the coning of the wheels, there is a lateral sway which is taking place because of the small difference which is provided between the rail head and the flange of the wheel. Therefore, there is a shock and vibrating condition which will get created when the train moves over those rails. Due to this condition, the track should have lateral strength, and this lateral strength comes from the web of the rail section, from the sleepers, the width of the sleepers, and the ballast cushion which is provided in the railway track. And finally, it should be having the materials or the components which can be replaced or which can be renewed as easily as possible with the minimum amount of the maintenance cost. And obviously, when we say about the maintenance cost and all these, finally the cost of construction, the cost of maintenance, or the cost of operation of those railway permanent ways should be minimum. So, these are some of the important requirements of any of the permanent way which is to be provided. Here in this diagram, a cross section of the permanent way has been shown. Here what we can see is that it's a single track condition, where this is the two rail sections which are being provided at a uniform distance, which is termed as the gauge distance. Then this is the sleeper provided below the rail sections, and on the side of the sleepers there is a ballast which is being provided. Below the sleeper section again there is a ballast cushion which is being provided. The thickness of this ballast cushion, as we have seen previously, varies from 200 mm to 300 mm. Then there is an embankment on which this ballast cushion is resting. In the case of the ballast cushion, the side slope is being taken as 1.5:1, that is from the stability of the slopes. In the case of this embankment fill, the slope is being taken as 2:1. Now we look at another slide where the single line on bank or double line on bank is being shown, where the bottom 1:30 slope is being provided for the drainage point of view. So dear students, today we have looked at some of the features related to the wheel and axle configurations. We have also looked at the track capacity and the methods by which we can increase the track capacity. And then we have taken the associated feature of the wheels, that is coning of wheels. Apart from these, we have also seen about the permanent way, their requirements and the cross sections. In the next lecture, now we will be continuing with the resistances which are offered by the permanent way and how it transforms into the tractive power or the hauling capacity of the locomotive. We stop at this point and goodbye. See you in the next lecture. Thank you.